Spice Math. That's right. We add it up, multiply it, man. Spice Math. Okay. A couple things we're gonna learn today. Spice Math. All right. Take some time, educate yourself. Spice Math. That's right. You won't believe it's just math. Come on.
Hi, I'm Ruth Doughton.
Hi, I'm Aaron Williams.
Hi, I'm Brandon Alexander.
Hi, I'm Kelvin Doughton.
Hello, I'm Lyndon Sincere.
We are your Spice Math tutors.
You won't believe it's just math. Just math.
Hello again. Today we're going to look at standard form. This is your mathematics tutor. And this lesson is targeted to forms 3, 4, and 5. And the topic is standard form. Now, this concept is a required concept for CXC, and it's also a concept that would help us to appreciate how very large or very small numbers can be written as a product. At the end of the lesson today, you will be able to define what scientific notation is or what standard form is. You will also be able to give at least 2 reasons why we use scientific notation. And then you should be able, at the end of the lesson, to convert standard decimal numbers to scientific notation. So let's go. A definition for scientific notation, otherwise known as standard form, is a convenient way of expressing a number as a product in powers of 10. And if you remember from a few previous lessons, we have discussed base 10 and the powers of 10. And today we're going to use those examples to see how we can understand scientific notation in the right context. On the board, I have some numbers: 413, 0.82, and 0.00631. Those numbers are decimal numbers, and we're going to use the idea of expanding numbers to see what they really mean. Because 413 came from 3 ones, or 3 times 10 to the power of 0, as we explained in a previous lesson, plus 1 10, or 1 multiplied by 10 to the power of 1, plus 4 hundredths, 4 times 10 to the power of 2. When we evaluate these and we sum them, we get 413. Now we can do the same thing with this decimal fraction. Understanding that the first place on the right side of the decimal point would be 10 to the power of negative 1, or tenths. And the second place would be 10 to the power of negative 2, or hundredths. So we can expand 2 times 10 to the negative 2, because we always start from the far right, plus 8 times 10 to the negative 1. Excuse me. The next number. That's a very small number. How do we expand it? How do you think we should expand it? Well, we use the same process with the powers of 10. That would be 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, 10 to the power of minus 6. So that's 1 times 10 to the negative 6 plus 3 times 10 to the negative 5 plus 6 times 10 to the negative 4. You would have observed, if you follow the pattern, that the powers of 10 increase as we move from right to left. So in the first number, we went from 10 to the 0, 10 to the 1, 10 to the 2. And if we had had more numbers, the powers of 10 would continue increasing gradually to accommodate all the numbers or all the digits in that number. Similarly here, 10 to the negative 2, 10 to the negative 1. It's as if we're counting along the number line. And the same pattern follows here. Now, scientific notation is a convenient way of expressing extremely large numbers or very small quantities. We have two numbers here. This is an extremely large number. Do you think you can tell me what it is? Most of us can count, or we are acquainted with the idea of a million or even a billion. Or lately, we might have heard about a trillion. What happens after that? How do you represent numbers that are much bigger than a trillion? Well, there's a nice little process you can follow, because after trillion, we go to quadrillion, then quintillion, followed by sextillion, septillion, octillion, nonillion, and decillion. If we have so many things to count, then we could use those. However, let's look at what's happening here. How many miles is this? 1,000, million, billion, trillion, quadrillion. This is 25 quadrillion, 300 trillion miles. Actually, this number represents the distance from Earth to the nearest star. But just by saying the words, we may not have had an understanding of it. Far less to write it multiple times. So we could use scientific notation to bring this very large number and cut it down to size. Or even this small number. Look at this. 0.00000000203. That's extremely small. But it's a time. It's the time it takes for light to travel from one side of an average room to the next. But does it really make sense? I have no idea how much time is this. I can't even comprehend it. But I can break it down into scientific notation so the number is easier to manage and we have less digits to write. We can do that by simply expanding it into powers of 10. How many powers of 10 do we have here? 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12, 10 to the 13. So this number is really 2.53 multiplied by 10 to the 13. I want you to observe a pattern. This number, the small one, is really 2.03, counting 3, 6, 7, 8, multiplied by 10 to the negative 8. So those are the answers. The question is, how did we arrive at those? What are the steps we can follow to convert a very small or a very large number into scientific notation? Let's go back to some of the examples we used at first. 413 was given as 400, 110, 3 units. When we convert that to scientific notation, we get 4.13 multiplied by 10 squared. I want you to try to pick out the pattern. 0.82 When this is written in standard form or scientific notation, we're going to get 8.2 multiplied by 10 to the negative 1. What about this one? 0.000631. When it's written in scientific notation, you're going to get 6.31 times 10 to the power of negative 4. And let's see if we could pick up the pattern that emerges. If you want to take a number from its normal form and express it in scientific notation, the emerging pattern is if you expand the number, the highest power is what will be used in the expression of scientific notation. In number 1, the highest power of 10 was 10 squared. In number 2, let's see if that pattern holds true. 10 to the negative 2, 10 to the negative 1. Which one is the highest power? Yes, you're correct if you guess 10 to the negative 1. So that's the power of 10 that's going to emerge when you're going to put that number into scientific notation. And the same thing happens in the third example. 10 to the negative 6, 10 to the negative 5, 10 to the negative 4. The highest power of 10 here would be 10 to the negative 4, and that's the number that emerges. The next part of the problem, or part of the solution, is how do we come up with the first number? We understand how to come up with the powers of 10. That's going to make our scientific notation possible. But how did we come up with the other number? That is the 4.13, or the 8.2, or the 6.31. You would observe again there's a pattern here emerging. All the first numbers, 4.13, 8.2, and 6.31, they're all numbers between a certain range. And in this case, they're all less than 10, and they seem to follow a pattern of being 1 or greater. So then, now that we have observed this pattern, we could create a number of steps for it. If I'm going to convert a number from its natural representation, for example, let's take another number, 3,150. Which one of these would have the highest power of 10? We know from positioning, the first place would be units, the second place would be tens, the third place would be hundreds, the fourth place, counting from the right, would be thousands. That's 10 to the power of 3. So we already have our factor. Then, how do we come up with the first part of the number? Well, if we follow the pattern from the examples, we must apparently insert a point, a decimal point, so that the digits in the number do not pass the value of 10. But the digits in the number should also remain just about 1 or greater. It means then, if I am to insert the decimal point in these digits here, it would have to fall between 3 and 1. So I'm going to get 3.15 multiplied by 10 to the power of 3. Voila, that's my answer. Let's do another one. Let's suppose we have this number. How do I express that in scientific notation? Once again, I look for the digit that corresponds to the highest power of 10 in that number. 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. Of course, as you go further to the right, they're going to get smaller. So the highest power of 10 in this number is 10 to the negative 3. Now to insert the point, where does it go? It has to go between the 4 and the 8. So we end up with a number that says 4.8. Yes, 4.891. Thereby fitting in number snugly between 1 but less than 10. Answer? Now let's see if we could put these steps into some rules. Because there's another general way you can look at it, and that is by moving the point a certain number of places. But in this way, once you can identify the power of 10, that's the highest value in the number, that is exactly where you need to start. So, let's look at another example. Let's try this one, 2.74. I want to write this number, 2.74, in scientific notation. So it must have a power of 10. That's one part of it. And then it must have another number that falls between 1 and 10. It can't be 10. It must be a little less than 10. 2.74. What is the highest power of 10 in that number? We have 10 to the 0, 10 to the negative 1, 10 to the negative 2. The highest power of 10 here is 10 to the 0. Since 0, by its place on the number line, is greater than negative 1 and negative 2. Now, I need to place the point so that this number is 1 or greater, but less than 10. As you notice, 2.74 is already within that range. So we simply write it over. 2.74 multiplied by 10 to the 0. But, as you would notice, 10 to the power of 0 has a value of 1. And if you multiply anything by 1, it remains the same. So the number 2.74, although it's written in standard form, in scientific notation or standard form here, it's actually the same value or the same amount we're writing over because we're multiplying 2.74 by the value of 1, which 10 to the power of 0 represents. Now let's try some. What about the number 295? How do you think we can put that into scientific notation? Or maybe we should review the steps. First step. For scientific notation, we locate the highest number or the highest power of 10. In this number, the highest power of 10 would be the 2 in the hundreds column. So how do you write that? That's 10 to the power of 2. 10 to the 0, 10 to the 1, 10 to the 2. Then, what's the next step? We place the decimal point such that the number we end up with must be 1 or greater, but less than 10. Can we place it between the 9 and the 5? No, that's going to give us a number that's greater than 10. So that wouldn't work. Can we place it between the 2 and the 9? Yeah, we can. Because When the point is placed here, we get 2.95, which fits exactly between or within the range that we spoke about. So 2.95 multiplied by 10 to the power of 2, and that gives us our answer. We have expressed the number 295 in scientific notation. In other words, in standard form. So we're going to put up an activity so you can try a few on your own. And remember to follow the steps. Step 1, locate the highest power of 10. And step 2, place the decimal point so as to create a number that's equal to 1 but less than 10. Okay? So generally speaking, scientific notation is really a way of writing any number such that we express it as a power of 10 and a number that lies between the number 1 and just a little less than 10. Let me thank you for tuning in today. We're going to put up some activities for you to try. And let me wish you all the best as you practice with standard form. Thank you. Have a good day.
You won't believe it's just math. Come on. You won't believe it's just math.